All right, so we've been talking about getting these black holes into the AGN disk, and so what I've been working on, we talked about a little bit yesterday, is essentially running an augmented n-body code that includes torque prescriptions, like what Betsy's been working with from Party Cooper 2010 mostly, and then also some eccentricity and inclination dampening forces and MRI as well. And so essentially it's analytic prescriptions put in this n-body code. And so we have a paper that's up on the archive that should be published shortly, under review right now. And so, you know, this is, I don't see the hats, but I'm going to put on my optimistic hat because of the mass segregation that we were talking about yesterday. We discussed that it actually might be likely that you could get a buildup of the more massive stellar mass black holes. So this is actually up here our most optimistic projection, where initially you have 10, 30 solar mass black holes within the inner 1,000 AU or 1,000 RG, because for 10 to the 8 solar mass black hole, they're roughly the same thing. Supermassive black hole, sorry. And so in a period of less than 50,000 years, they because of these migration torques will migrate towards this migration trap at 670 AU, and on the way form binary. So every vertical dashed line is a merger, and so and this key over here is the final mass of a black hole. So you can build up to 240 solar mass black holes. You get a lot of other interesting dynamics on the way, and you do end up with several resonant orbiters. So, one of the questions we ask is, how do you break this resonance once you have it? And so then the idea is, right, you will continuously get additional migrators coming into the inner 1,000 AU of the disk. With what Saida and Gaia spoke about earlier with grind down, right? It's actually the timescales for grind down suggest that right around 1,000 RG is actually where you're going to get these objects being ground down into the disk. So if we drop in objects, so this really chaotic plot here shows that over 4 mega years, if you're dropping in every 100,000 years or so another stellar mass black hole, you actually over time can break these resonances, and so you'll effectively get however much mass you put in over time will effectively make a black hole, and you can get up to several hundred solar masses over the course of a few mega years. And so that's the basic concept. I'd say I want to point out another thing we're thinking about has to do with chi effective. And so we've been thinking about when these binaries form, if we can trace them just a little further past their formation and look at the direction of their rotation relative to their direction of their orbit around the supermassive black hole. So is right, all of my orbiters, right? But once these binaries form, occasionally you can actually have these binaries rotating in the retrograde direction, and so that can have implications for the spin, for the chi effective once they merge. And I think probably Barry and Savik could talk about that clearer than I could, but that's another thing we've been looking at. So, done some work on actually putting this idea into practice and saying, if we give it some migration forces, if we give it some gas dampening, and we run it through an n-body integrator, do we actually, see what we suspect we will? And so, yeah.
Can you tell folks what optimistic assumptions we've been assuming for these mergers?
Yeah, that's a fair question. So we've been very optimistic about them emerging. Right now, many people in this room work on, once you form a binary in a gas disk, what does that look like? And so we aren't actually at this point resolving what that looks like. We're saying if they pass each other within a Hill radius, and if their relative kinetic energy is less than their binding energy, then we're saying that's a binary. And then we're saying there's going to be a lot of really interesting gas black hole interactions within that Hill radius, and we don't know what that is. So let's say they're merged. So to be clear, what we're doing is we're really just showing the formation of binaries. We have a few analytic arguments that would say, sure, they might merge, but I don't think we're making a super strong statement saying that these mergers will happen. But I think we can say that we can get hierarchical binary formation at the very least.
Could you also take like the pessimistic case for pulsar timing arrays, for example, where even if the binaries don't merge due to gas, a third one comes in inevitably, so you'd expect that that would drive the merger on a different time scale.
Yeah, I mean, right, that could be the case as well. But we're just trying not to necessarily make a statement because there's a lot of uncertainty there. But yeah.
Just following up on Andrea's point, yeah, there's a lot of fun dynamics that's going to happen, as you gather all of these masses. You can imagine that instead of merging these things, you form these binaries, and they encounter each other, they'll, flip partners, there'll be scatterings, there'll be all sorts of interesting fun in that region. So, detailed simulations to kind of, to follow up on that and include things like feedback and more realistic torque prescriptions are totally the way to go.
You go ahead first, yeah.
But I think, that's a tertiary SMBH for to drive PTA detectable mergers. So, these are just stellar mass black holes to start with. Obviously in this example that Amy showed, they're kind of on the massive side, but LIGO says they really exist, so why not? And then the black holes that she's dropping in are also still stellar mass. So just assuming that there's stuff so to Brian's earlier point that like more things are coming, there's more stuff in the outer disk, which is true, and then the migration torques will drive them in. So then that has the dynamical effect of disrupting what was, would otherwise have been a stable orbit if you just left it alone.
Yeah, sorry. Yeah, to clarify that. And it's also the time. It all depends on the merger time of these binaries. If the merger time is long, sure, you could get a tertiary encounter. But for the most part, if you assume a shorter merger time, by the time a third body comes in, it won't be massive enough to kind of break the hard-soft boundary for a lot of these binaries, assuming that they're at least in spiraling at a high rate. But I think a lot of us would agree that's to be determined. So.
Okay. Thank you. Let's see. Just got to get one more. I have to. Okay, vlog. I'm going to try to download this, but there we go. There you go.
Right. So much has been said here about the gas flow onto the orbiter. So I wanted to show some of the new stuff that has been coming from the field of protoplanetary disks on this issue. So the general idea of the accretion onto an orbiter in 3D would look a bit like this, right? So you have that the accretion is not going to happen in the mid plane, but then from the the poles. That means that you cannot run this thing in 2D. That's a waste of your computational time, right? So,
Thank you, Vlad.
wow. So this is how it was seen, actually. So this is an actual star, right, with an orbiter that was seen then for the first time last year. That's EDS 70. And what you're seeing here is a planet. So it's seen for the first time in a disk. But the emission that is seen from here is most likely not the atmosphere of the planet itself, but a disk, right? A circumplanetary disk, as it's seen here in this video that's looping. So this is a video from this model here. So this is a model, one of the most high, well, I mean, like one of the highest resolution models that has been done. This is done with nested grids. So the planet should be around here, and I think that this model here has at least 4 levels of refinement. So in the finest one, the element, I mean, the grid element is about the radius of the planet. As you can see there, the temperatures, well, I mean, it's not show the temperatures here, but they do get quite high. So you can see here the flow, right? It is getting from the disk into here, and then you also have some winds happening there because it's quite hot. Sorry?
Is this magnetized?
No, it does not have magnetic fields. There are models with magnetic fields, but not to the resolution that this model has. Plus, in protoplanetary disks, at least we do not expect, right, much magnetization to happen there. So this model, yeah, is I would say it is more accurate. So this is another model that was trying to reproduce this, and it did that with a planet about like 3 times the mass of Jupiter. And I would like to highlight this because this was ran for 4 million years. It carves a deep gap, and this planet is not seen to migrate. Right? So type 2 migration, as we understand it, is not happening in this case. And we don't know why. Yes?
When you say we don't know why,
Yeah, we don't know why.
it's a simulation.
Yes.
So you can know everything about
They
it.
didn't look at it. They published it, and then it was pointed out that this planet was not migrating, and they didn't know why. So that means that someone else has to run it and try to see what's happening here. But one thing that they notice is that the gap here is quite deep, right? So the regions that would give you the torque, they don't have gas anymore. So then, yeah, the magnitude of the torque goes down quite a lot.
What's the mass ratio?
A few times 10 to the minus 3. Yeah. So I think it was like 3 times or 4 times 10 to the minus 3. Yeah.
I can start the thing.
So this is really cool. I'm just wondering if we sort of took this analogy for AGN systems, and we say that accretion happens not through the midplane, but it comes in via some polar flow. Essentially, we want to think of our embedded accretion disks as kind of at 90 degrees to the rest of the disk.
So you'll get some really cool feedback effects into
Wait a
the
moment.
plane of the.
No.
Right?
It's right here. It's, the flow is, this is the disk midplane. The flow is just coming down like this. The disk isn't flipped itself.
Oh, I see. Sorry, I thought the flow was coming in at the pole. Sorry.
It is.
Right.
Onto the
yeah,
disk.
it is
Oh,
coming.
onto the disk. I see. Onto the mini disk. Gotcha.
This
Yeah,
is,
it goes from the midplane onto the pole and into the disk.
Okay.
I think in some studies where people look at the torque as a function of the perturber mass, you do expect the torque to decrease for the higher masses. So I didn't have a complete thought there. I just thought I should fill in the silence. But I mean, maybe it's not surprising that as you get more massive, you carve a deeper gap and it's harder for gas to flow across. Any
Sure,
thoughts?
yes. Well, I'm thinking. So type 2 migration, as we understand that the migration rate depends only on the disk mass, not on the planet mass.
The ratio of the,
No,
my
because
understanding,
what would happen on type 2 is that the planet carves a gap, it decouples the inner disk from the outer disk, and then the planet locks to the disk, and then it migrates in at the viscous rate, right? Which I know that there are new works that claim that that's not the case, right? Because you can mix gas from the outer
Right.
disk to the inner disk.
yeah.
I'd say the jury would still be out there to check that and see if that's really the case. Uh-huh.
we covered the other night.
Clarification. So is the one where on the right is that a live binary, and what is the
Yes.
and then what is the mass ratio of the planet
As
to
I was
the
saying,
disk
that's-
No?
Yeah, it's a few times. Oh, to the disk. No, to the star, it is about a few times in the mass. For the disk, you would have to integrate here. I mean, it's given here what the surface density is. Do not know that number from the top of my head.
Can you walk us through these arrows on this green
Mhm.
figure? Could you walk us through the arrows on the green figure?
Mm-hmm.
Like to show where the gas is flowing, because I'm a little confused.
These arrows are. So the planet is in here, right?
The other thing is not a planet.
No, the other things are the resonant points of the planet, I suppose. I'm not really sure what they mean.
Like there are a few singular points on that figure.
Yeah, exactly. Yeah, it's a pam, pam, pam. Yeah.
So
Yes.
what are those things?
I don't know. I would imagine that they are the resonances, right, that are set by the planet.
You get
But I'm not
those
sure.
in the 2D. You get to see them because as the orbiter is moving around, it creates the density waves. So it might be like the
The
valleys,
Lindblad locations?
the
Possibly.
valleys of those waves.
I would need to look at it. But I was wanting to highlight where the arrows here, right, in the location of the planet, which would match the cartoon that we had up
So
here.
some arrows seem to be pointing away from the planet.
They do, yes. In this region, you have outflow.
Of more concern to me even than that is, I guess the one thing that maybe, I don't know if this is what's catching your eye as well, in the outermost green point, that one, yeah, it looks like every arrow is going away from it. So how can that be stable? Am I not seeing it
Divergence.
correctly?
It's in a cavity.
It makes sense, actually, because that's what you expect from resonances, right? In,
Okay.
well,
Yeah, that's where the torques are going. Okay,
Yeah.
that makes, okay, yeah.
Yes.
Yeah, I'm still trying to process this because it's. So I'm trying to understand how the gas flows within the Hill sphere. So I can see an inflow and an outflow in the midplane, right?
It's the Hill sphere.
Yeah.
Yeah.
And so you're driving an outflow at the boundary of the Hill sphere into the rest of the disk. That should cause turbulence, and some of that gas should end up coming back in, right? It's self-limiting.
Traction.
Yeah. So you'll get little convective flows on the boundary of the Hill sphere here.
Yeah, there is a meridional
And they then
flow.
collide.
Yeah.
Yeah, okay. All right, cool.
Thank you. We have to look forward to as we zoom in on these things. And then, of course, we're going to shine on this.
Yes. We haven't talked about radiation. I'm wearing my pessimistic hat at this point.
Oh, that's, yeah. Other.
Yeah.
Oh, yeah.
Okay, so this is not my slide. This is one of our students, Andrea Mejia, who unfortunately is taking an exam right now. So she would, I'm sure, vastly prefer to be here, but this is basically a similar setup to the one that Betsy showed, but here what Andrea has done is she has on the top just a fixed prograde orbiter, and you can see that the results look very like Betsy's
No, I don't think that is fixed.
density
It's
plots.
integrating.
Oh,
big
you're
are
right. These are live. That's right. These were live. Okay, good. So, yeah, because the torques are much bigger. So, just to answer the question of how bad is it an approximation if we just take one object and we treat them each in isolation. She ran one, and you can see this is the torque over 30 orbits. And then she ran two with one of the objects placed in the same starting place as the single object, and then there's another orbiter further out. And this is the torque on the one object, and this down here in blue is the torque on that essentially same object when there's a second object further out. And you can see, it's a little bit hard to see on the scale here, but it's sort of the magnitude of the torques and their oscillations are not dramatically different. They're not dramatically altered.
Numbers. It's
Oh,
very
sorry,
small.
you can't see them. Okay, so so this is like negative 20 to 20 and 0, and here is 10 and negative 5. So you can kind of see these are sort of sticking between, it's slightly positive, but it's sticking sort of under 15, and here it's also sort of sticking under 15. So we're in roughly the same neighborhood. There's not a qualitative difference in the behavior. If you actually take one and subtract it from the other, there's some little hiccups and wiggles that are slightly different, but it's not a fundamentally terrible thing to treat them separately, at least for sufficiently well-separated objects. These are obviously not anywhere close to forming a binary with each other, but the migration torques don't seem to be dramatically altered by the existence of other objects in the disk.
So what is the LIGO in the title, like how this is going to evolve?
Oh, sorry. So this was part of a series of arguments constraining LIGO and how can you what can we say about building up stellar mass black hole binaries in an AGN disk? So all of our prescriptions. So for example, in Amy's work that she was showing, she's assuming these kinds of torques, but she's putting more than one object in the disk. So is that okay? We did not know that when Amy started doing her runs, but Andrea says, yes, it is okay. Yeah?
I want to say, because Amy,
Mike.
you're using constant.
Mike?
Oh, yeah.
You can correct me, but I think Amy's prescription was that she has like a constant torque for the migrating ones, and that's one of the things we found out with the hydro, that it's oscillate. Like the torques are actually changing over time.
Oh, yes, that she's using a fixed, yeah, she's using, sorry, that's true also. She's using the assumptions of a fixed orbiter to calculate the torques. But if you put in a live orbiter, the torques actually are larger. So Amy's is, in fact, you know, they probably move more and faster. But broadly speaking, assuming the torque that's appropriate for one object and applying it in a disk where there are multiple objects is probably fine, because it doesn't, you know, in detail it might change, but in the broad scale of things, it does not. It doesn't change the rates.
Andrew already mentioned this, but I might have missed. So when I run simulations of, and this is just not live planets or black holes, but when you place them in the disk, I have to run for like over a viscous time to see the torque settle. And what you do see like oscillations, and they're all numerical, and the torque rises and then it drops, and then eventually it converges to some value. So are you cutting off the beginning of the simulation, or is this still the initial settling of the disk?
We are still watching the initial settling because we don't have the time to run for,
Right.
you know, it's
especially for a
computationally
live, yeah.
intensive for 2 live orbiters, so.
Right, and for the live ones, you have to assume something about the density of the disk. So is it fair to say that the torque is stronger because you have to normalize the density to some
Yes.
value, and we don't really know what that is, right? So,
Yes, correct, yes. All of those things, yes.
So this is helping LIGO, right? This is not constraining LIGO.
Constraining is correct.
Okay.
Thanks for the guidance to where we need to go. Any other thoughts on this one, or should we move on? Okay. Oh, yes?
That's such an interesting thing. And yeah. In several of these ideas, you get these resonant chains, right, that you mentioned. So if you put it in the hydro, you get the torque themselves might resonate with each other. You have a very different evolution than even discussed here. You might, so it might be interesting actually to redo this thing, but now with resonance based.
But of course, then we also need to put in MHD so that we can get the turbulence, which breaks the resonances, because the resonances are only so deep and you can jitter out of them.
You can also break them with n-body. Oh, no.
Okay, you can also break them with n-body interactions. Tertiary interactions. Okay, the next one is you again.
Okay, all right, so this is.
Sorry, I put Saab together.
So okay, so this is my slide. This is a very simple slide in the sense that I have done something very, very literal-minded. So I think it's come up before. There's this lovely Barreto paper from 2011, okay, right order of magnitude. And where they model these 2 O stars in a binary in a medium that is differentially rotating. It's meant to be a simulation around Sagittarius star. And they find that the orbital halving time in that medium is 1,000 orbits of the binary around its center of mass, around its own center of mass, or if it's a prograde binary, if the binary is rotating prograde, and 200 if it's retrograde. And so what I've just done here is I have taken that extremely literally, and on this vertical axis I've plotted log of 1/time, just so that the thing that is on the top is the dominant effect. Okay, so it's got the shortest timescale thing is the thing that is on the top. And I've plotted the gravitational wave timescale in black. And then I have assumed that the Barreto result holds for many, many orders of magnitude, many, many halvings, like 20. And just said, okay, so what does that mean in terms of how fast these binaries harden to merger and comparing that with the gravitational wave result? And so, as I said, a retrograde binary hardens faster than a prograde binary, but it's just a factor of 5. And then for reference, I've also put on here, this is for assumed GW 150914 here, I've put on the LISA frequency band and the LIGO frequency band, and figured out how long it takes to get from here to here. And it turns out that it takes a mere 11 hours if you have a retrograde binary, and you actually can follow this prescription all the way down. Obviously, that's a debatable proposition, but
No, it's not debatable. It's impossible.
but I would just like to point out that there is the potential for these things to pass very quickly through the LISA frequency band, so quickly that they become undetectable, because LISA is counting on being able to build up, a year and more signal of a binary, of a stellar mass black hole binary, in order to be able to detect it. So if it's only there for 11 hours or 56 hours, then it just won't be seen. But on the flip side, of course, if that is truly how efficient the hardening is or something like that, then you might expect to form intermediate mass black holes pretty efficiently and effectively. So then since you're doing this in an AGN disk, which has an SMBH at the center, then you've got yourself an IMBH SMBH binary, which means that you will still get at least a signal, which is good. I guess just to also point out, so I've got here in dotted line, just sort of for perspective, if you assume that this is around a 10 to the 8 solar mass primary, and this sort of halving is happening around a 10 to the 8 solar mass primary, and you have a migration trap at several hundred RG, then for a binary, for a GW 150914 binary sitting at that migration trap, this is the Hill radius. So you become a bound binary, and the gas hardening timescale is even here, just the halving timescale is very much shorter than the AGN lifetime. So, and of course, I think at this point sort of infamous, here's a Hubble time, right? And so the same binary in the absence of gas goes nowhere in a Hubble time, and the binary in the presence of gas is clearly going to harden via the gas much faster than in the absence. So, and over here, this result is probably just fine, right? In that region for sure.
So to turn this around, if you cannot see this in LISA, but you see something in LIGO that you should have seen in LISA, you can say that it's an AGN, right?
Correct.
So it's great.
Yeah.
Actually, I was going to make the same point with the caveat that I can think of 3 ways you can do that. One is this: it moves too fast that you can detect it in LISA. One is it's so eccentric that it peaks in its power peaks far of LISA, and 3 is that it actually forms at that frequency. So you can think of it's still informative comparing the 2 catalogs.
So of course, I'm extremely skeptic if you can actually put it at these levels, because you won't have any gas in these very small scales. And you need a comparable mass to the mass of the black holes to actually continue something like this. So I don't think so. But if it worked, interesting thing it would be, we actually have a simulation of inspiral in gas. If it's so fast and it's dominated by gas, the inspiral is so fast it cannot be on circular orbit. It would be extremely eccentric orbit. So once you get to the LIGO, it would be potentially still be highly eccentric. If it's so fast, it should be still potentially be still highly eccentric in the LIGO band. So that's just an interesting aspect of that. But I still don't think it's
Well, right, yeah, no, I'm definitely, yes, this is a very, very big extrapolation, but I'm curious. I guess I don't understand why it has to be eccentric if
It
it's.
looks like this. Okay, it's not like your usual evolution if you think about it. It's like anti-spiral, extreme spiral thing that you see. Okay.
On that time scale? I mean, you're still getting
if
orbits.
in your merger time scales, okay, I'll start to become comparable to the orbital time scale. Okay, then it means that it couldn't be on circular orbit. It would be really this kind of a spiral thing, direct spiral in one spiral in almost.
Oh, but it's not quite, right? Like the assumption that's underlying this here, and this is the assumption that goes all the way down, is literally just so whatever the semi-major axis is of the binary, I assume that 1,000 orbits or 200 of those orbits later, the semi-major axis is half. Right? So you're still getting orbits. You're still getting, I mean, these are still real orbits. You're just passing through the frequency space. I agree that they're in some sense, they must be a greater departure from circular orbits than they would be from gravitational wave emission alone. But I mean, the last few orbits that LIGO detects are, sort of not circular in that, like its semi-major axis is coming down very quickly. So, but it's not, I wouldn't necessarily assume that these are eccentric per se. Like maybe they are, but I don't understand why that has to be the case, or that you would want to characterize them that way. And then it would change the wave, like in particular, right? Would it change the waveform? Like how does the waveform change? If a waveform is already, like that, I don't know, did you have something to say about that?
Well,
Yeah.
I'm not sure how you squeeze it, but I don't understand the numbers. This 11-hour number.
Yeah.
The AGN lifetime on this plot is presumably, so if you look at the plot in the Lisa band, the AGN lifetime is presumably corresponds to 10 to the 7 years.
Yeah, so it's between 10 to the 6 and 10 to the 8 years. Yeah.
So if you take the upper part, it's 10 to the 6, and that's like 10 minus 12 and a half. So if you go to -5, that's presumably 7 orders of magnitude faster, so it's about a year.
Yeah.
So how?
Oh, sorry.
So I don't understand how it's 11.
This is the traversal time. Sorry, it's not the traversal time from the Lisa band to the LIGO band. It's the traversal time across the Lisa band.
But most of the time is probably, most of the time is always spent at the very beginning. So I think it's the same.
No, wait, hang on.
I just don't understand the 11 hours.
Hang on a sec. So this is 10 to the, so that's 10 to the 6. Yep. And that is. Minus. Yeah.
Okay, maybe we should.
All right.
solve it offline.
Yeah. Let me double check it. Yeah.
Very quick comment.
Yeah.
We have time. Yep. So, just in the spirit of, looking at what we need to do going forward to analyze this channel properly with LIGO, we're starting with kind of cartoon versions of things. We're seeing that there's a ton of work to be done on all aspects, on all parts of the elephant that we're kind of trying to grasp, right? And I think in a few years, I would like to see how such a naive extrapolation changes when you throw in accretion in 3D disks with feedback. And right, I'd like to see how this naive picture is altered. So,
That's why we've called you all here today.
Yes.
Okay, let's see. That's Andrea. Do you want to come up and talk a little more about what kinds of migration rates you're seeing with these models?
Should I come up there?
Yeah.
I just would mention one more point. So we don't assume a surface density since we don't have a live binary, so you could scale it to whatever you want. One thing I really wanted to stress that we haven't totally touched on is the sensitivity of your torque to parameters. So, for example, I just looked up the Mully paper with the type 2 migration. They have a viscosity of 10 to the minus 3, which is really low, which I think you might expect in protoplanetary disk. Right. But so I don't think there's any surprise that they wouldn't have that much gas flow into the gap, for example. But for example, I didn't want to show these preliminary results, but I can tell you if you say you increase the mass of your perturber by just a factor of a few, you can all of a sudden have a negative torque, right? So in this region where you start to carve a gap, the torque is highly nonlinear. And there's also a sensitivity with viscosity and Mach number, for example, H over R. It all plays a role, and so if you have this one result here, you can't really apply it to everything else. You kind of need a whole consistent picture, which we don't have. So I would just add that to the list of things to do.
Which is to some extent what Particooper started doing.
Right.
With and deriving the analytic formulae, but that was
Getting
also
some
in
scaling
a very
relations.
Yeah,
really
in a very
useful.
simplified
Yeah.
situation. So do you have yet a feel for how strong these torques are on any sort of absolute basis?
So I can compare them to the viscous torque, for example, and they're less
Okay.
than that.
Mm-hmm.
It's hard to compare. If I were to compare, for example, to like the Tanaka type 1 formula, it's not the same regime,
Right.
but
right.
it's order of magnitude less, but it's not really a fair comparison to
Right,
make.
because this is a gap opening
Yeah.
object. Okay, great.
So what leads to
Give them the mic.
once again, what leads to the torque flipping positive in your case?
Becoming positive
Yeah,
here.
yeah.
It really is just something to do with this. Am I attached to you? Okay. Something to do with the gas flow from the outside of the gap to the inner disk. And that's not something we haven't looked at streamlines in
horseshoe?
particular, so, sorry.
The horseshoe drag?
Yeah, so so for some reason, gas spends more time or it piles up in front of the black hole. But this flips around and changes if you have a slightly different viscosity, for example. So basically, and there are oscillations in the torque on really short time scales, as Andrew mentioned. So this could just have to do with it's just not a perfectly spherical flow.
Yeah, but if you have a deep gap, then the rotational torque has almost no inertia, right? Because there is not much gas there. So I don't see how its impact on the total torque can be that high, unless of course.
It's comparable to the torque from the rest of the disk.
Really?
Yeah.
Even though the density is like extremely low.
I mean, part of it is because it's so close, it ends up exerting a really dominant component, right? Where the gas elsewhere might exert a strong torque if you were next to it, but it's farther away.
Well, then you need alpha values that are extremely high for that, right?
This is off of 0.03. You also see it, yeah.
0.03.
Yeah.
Fully ionized.
3 times 10 to the minus 2.
Yeah.
Okay. Even for the MRI, though, you expect alpha 10 to the minus 2 or so, no?
We have runs with 0.01. You see the same thing as well. Just the magnitude of the torque shifts a bit, but you still have a positive component in the Hill sphere.
Just want to make a general comment because two people mentioned this notion that if you have very little gas near the object, you can't significantly torque it. I think that's not actually a right way of thinking about it, because you would need comparable mass to the object if you want to drag it on its dynamical time. But we're comparing it to something which is much, much longer, like even the gravitational in spiral timescale is, I don't know, 10 to the 5 orbits for stellar mass objects. So even if you have tiny amount of mass at any given time, torques are very relevant.
I was going to talk about that tomorrow morning, but yes, the torque it's tiny. Yeah.
Luciano? He's gonna come up.
Yes, I will repeat one point made by Barry that we discussed together. But also I want to show you some results of the effect of feedback in a binary embedded in a gaseous environment. It's a work I have done with Marta Volunteri. And what we have done is evolve a binary in two regimes. One is regime of here, in which you have a binary embedded in a circumbinary disk that is so hot, this one, that the gas is so hot compared with so the Mach number here is comparable to 1, so the separation of the binary is compared with the thickness of the disk here, that the binary is not able to open a cavity. And then we have other simulations in which you have this cavity around the binary. And we have run the simulations with feedback in both supermassive black holes. These are supermassive black holes, but can be used to stellar black holes. So we put the feedback coming from the accretion of these two bodies, and here are what happens if you don't have an initial tidal cavity, like in this regime, then winds coming from the accretion push away all the gas around the binary. So you stop any kind of torques that come from the gas. But if you start with this cavity, then like winds escape perpendicular or parallel to the angular momentum accreted, then goes up toward the cavity and escape freely from the disk and doesn't perturb the disk. So if you look this case in which you have a binary embedded in a very hot medium, that this, I think, this is my guess to what you will have for a stellar binary inside an accretion disk, something that is super tiny compared with the thickness of the disk. If you put the feedback here, then this is what happened. If you put the feedback, the separation stays more or less the same because you open a feedback cavity. But if you don't have the feedback, then the migration, this separation of the binary over time, separation decreases very fast. And this happened because the binary excites a ellipsoidal perturbation in the disk that has a principal axis that lags behind the principal axis of the binary. And this difference in the angle, this difference between the two principal axes, flows a torque, a gravitational torque, that is super strong and drives the binary. But this result of the feedback of what can do for the case of stellar black holes will depend if we form an accretion disk around each stellar black hole. And this, we go here down. Do we expect an accretion disk around each stellar black hole? Well, will depend. And one quite interesting result is comes from simulations of common envelope evolution. And I think that is worthy to look what they know about the evolution of compact objects, because this regime will be, I guess, very similar to what would happen to stellar black holes inside an accretion disk. And in this case, they have evolved one binary, and they have seen how the gas that falls toward these bodies behaves. And they look if they form an accretion disk or something that is rotational supported or something that is more disordered. Okay? And they have changed. Here you have the fraction of matter that is in a circular orbit at the end, and the adiabatic index. And the adiabatic index is telling you how large is the compressibility of the gas. So for large compressibility, so for gamma smaller, closest to the isothermal case, you have a lot of the gas that will fall towards an accretion disk. And if you increase this index, at some point you will have only disordered orbits. Here you will not have the formation of an accretion disk. And that in that case, maybe you will not have the associated feedback coming from the accretion disk. And then you will have something more similar to what Barry was talking about. And if you put it in a way of words of optical thin and optical thick, it's only a cartoon showing that if radiation can escape from the accretion disk of the supermassive black hole, then the stellar black hole may form this accretion disk, and if not, maybe you will have this convection dominated, or maybe, I don't know, this radiatively inefficient accretion in which you eat almost all the radiation that you produce. So, and having an hyper-Eddington equation. So the point I want to make here is that my guess is that the evolution will be similar to this type of evolution in which you have the two bodies embedded in like a cloud of gas at the end, and that we have to we will have to be very careful on how gas will fall towards the black hole, because then this will determine totally the mode of feedback that we have. Because in this case, I assume the formation of an accretion disk around each black hole. And here I put the winds and the radiation coming from the black hole. So it's a difficult problem when you have optical thick medium around the stellar black hole.
That's really cool. This comes back to Dan's point earlier, what is an AGN? So what are we embedding the stellar mass black hole in? So it may be that we end up with different interesting modes of accretion depending on the system that we throw these things into. So stellar mass black holes in quasars may have a very different effect than stellar mass black holes in, you know, lower luminosity AGN or Seyferts or something like that. So it depends on your model. Yeah, things are getting complicated.
Yeah, maybe in, like you say, maybe in low accreting supermassive black holes you will have something more like this, because the accretion disk will be less dense at the end. Will be more optically thin to the radiation of the accreting material toward the stellar black hole.
Right, and that'll give us better EM counterparts.
Yeah, you'll have a better EM counterpart, but maybe the torques will be less efficient,
right.
And so you will have a contrarrel correlation between gravitational waves of these stellar black holes and the radiation coming down.
I just have a quick question. Can you walk us through those red clumps on the diagram for gamma equals 1.1 and gamma equals 4.3? Because I don't understand what's happening in those pictures.
Okay, in these pictures, okay, these are, well, I only put it here to show you how nice, like circular rotational support material you have, but these are different orbits of different portions of the gas that are falling toward the black hole. This is, in this case, okay, the experiment is you have a point of mass, that is a zinc particle, and you are moving it through a wind, and you have a gradient of density that is modeling the evolution of this body surrounding a common envelope of another other star. And then you have different portions of the gas that are falling towards the black hole, and all of these have an angular momentum that are parallel. So they form this accretion disk. But in this case, you have a lot of the orbits, the angular momentum is not correlated, it's not parallel between them.
So those red threads are orbits of individual
orbits of individual parts of, yeah. They have different impact parameters. That's the thing. So the orange one are smaller impact parameters, and the more purple ones are larger impact parameters, so further away. But all they fall in something that is like an accretion disk in this case. And these are, this is here, so here you're only taking the portion of things that with momentum angular that compared to the Keplerian angular momentum. That is bigger 2.1. So this is the fraction. And so they say that at 1.33, that is 4/3 gamma, the adiabatic index, then you have something that is not sustained by rotation. So you will not have the formation of the accretion disk. So you will stay with something that is more disordered, and the accretion, well, you maybe will not generate this accretion disk.
What are the temperatures in the inner parts?
The temperature, well, no, really. But again, yeah, this is a paper of Murgia and Berthier, and I can show you. I have it in the laptop.
Yeah.
Just what Barry said made me think. So he said you could get a different, essentially, answer if you place your black hole in a different type of AGN disk. But I'm wondering, the energy kind of injected into your disk from one or many of these perturbers could also alter your energy equation in a way that you change the overall accretion mode of the AGN. I mean, this isn't based on any type of calculation. I'm just wondering if it's an interesting thing to think about, because I've been thinking a lot about how, exactly what Barry said, how kind of the binary throwing a perturber into the disk changes when you have an 8F versus a, say, a more Shakira-Sanyaev type model. But perhaps you maybe even can change this overall accretion mode. Just posing the question, I don't know.
Okay. You say the accretion mode of the stellar black hole or of the big? Okay. Yeah, locally maybe, yeah. Maybe if you're in a vector-dominated low accretion rate, maybe, yes. The effect.
Add enough heating to that area that you change from a thin disk type accretion mode.
To affect this, yeah. Yeah, maybe, yeah. Yeah, I guess, no. No, I don't have a guess for that. It's difficult, yeah. Yeah.
Okay. We're just about, I'd say let's take our coffee break now and then come back for discussion and, where are we going from here? So maybe come back at 2:25 instead of 2:30? 3:25.
My Mets hands firmly
I have an answer. I need to read my own labels. The time scale that I listed is the halving time scale, which it even says T half is lot. I feel like not that would be appropriate for the having a time scale on top of it. But it's about a million seconds. I feel like I'm just for now. Like it's about a million seconds to merger, so it's about a month. Okay. If you follow the gas pattern way down. Because I'm not subject to. Oh my gosh. No, it's even dumber. So no, it's not. I know. I mean, he's smart, but I just did a dumb thing, and I said. For concatenated objects in a binary in a media.
Okay, yeah. Well, I could certainly,
Not totally I could off of what an AGM disk just passes.
That's what.
In fact, it's a little low for AGM disk density, but let's just go with it.
Oh, so you said it's brighter than 20th?
That his simulation shows that the binary semiconductor axis has 1,000 like this.
Well, it's, yeah, yes, on the order of 100,000.
Binary.
Yeah, I'll check.
In that paper,
In 18th magnitude? Yeah, I don't know, tens of thousands, I'll check. Okay. But I can do that.
But he just comes up, but they come up with it from, he's not writing it, right? Like he's not saying.
I know, in
Yeah,
the simulation,
yeah,
there's a
yeah,
section
yeah.
where they say degrees will be
Yeah.
I think the issue with that on your example.
Yeah, let me get that, like, let me run to the bathroom.
Yeah.
And I'll get that real quick, so. And you will work with that.
Paragraph by paragraph.
Yes.
Okay.
Yeah.
Oh, that's right.
So you're gonna lose it at
She's
some.
Oh, cool, okay, yeah.
So you're gonna lose it at some, so I should calculate what the semi-major axis is where you lose it basically. Population, viscosity, gravitational. Yes, yes, although it's been a long time since I read it, but yes. Sure.
Black, the gravity.
Yeah, absolutely, yeah. Yeah.
Yeah, pretty much, yeah.
Right. Yeah.
Also,
Yeah, okay, yeah.
hydrodynamics are kind of put in terms of, right, so it's constant, there's no interaction because it's just, a set of, formula based on, radial position. So, while the end body gravitational force are fly, everything else is just prescription. So,
Well, it's trivial if you.
so you know, if the gas is.
Or I don't mean, sorry, I
That
don't
makes
mean it's not, I don't mean it's not trivial to calculate.
Yeah.
Not
No,
a
this
trivial
one is not
impact.
trivial. So, you know, sire.
Yeah, sorry, sorry.
It is the sire.
Okay.
We should actually slow down.
Like, well, striker, no, is from, starting for 20 minutes, actually, to give a static.
So if you assume no change to the DC structure,
Okay.
then you just multiply by 1 over the mass. Right? Then if you assume there's a pilot, still less.
I honestly
mass.
don't know, I
1 over
haven't,
the mass would be the
I haven't read the other papers, so I don't know.
what I think will show me.
But yeah, it's just,
Yeah, I'm extrapolating this all the way down.
I think you're taking the blue.
Yeah, extrapolating it all the way down, right.
If you go to 1,000, then you have to see.
Yay.
So you have to go. Then you get a tiny number.
So the color is,
If you do that, right. You don't get such a tiny number.
Then you get it's like amperes or
right, so it includes.
Wait, this doesn't make sense. Because there's something here that says,
But it's mainly,
as we decrease the mass of the
and,
then you are,
it's different from what? Increase, yeah, somewhat, right.
where are your transitions?
Due to
Oh, in Churchill units. Okay.
That's,
Yeah, of course. It'll be. Well, it's Churchill of.
It's our criteria.
Oh, no, but it's Churchill of this thing, not Churchill of.
Low relative.
There's no central option, right? These are two FMPs.
Our transformation.
So it's the Churchill reading of this.
No.
So yeah, so they're pretty hard. You would need something significantly, you know, at least
Why is it?
mass binary, not
You're asking why is it?
binary.
So I would expect, right, that
So we predict
these could get closer together. So because this is less massive, then this should be able to get closer together while still enclosing more mass than that.
I don't necessarily have an
In
number,
like,
right?
meters.
Oh, but
Because
if there's separate, so yeah.
there's less mass, like if it's the same density.
When their neutral radius
What is not?
which is on the order of QA.
These are three formers.
Right, we assume they merge just because, you know,
Wait.
gas, we really, gas.
But this is, so this is a 10 to the 3 solar mass binary. That's the whole mass difference. Okay, that's what I first thought, but then you said that there's a central supermassive black hole, and then I was like, wait, what? Okay, got it. Okay, now I think, now this makes sense. Okay. So yeah, no, I agree. I'm extrapolating
What I'm in here.
You can multiply by the 1 over the mass. Black hole around.
This might actually be different for this.
Are you gonna be back tomorrow?
Because
So my notes.
than here.
Okay.
Because the disk, so in this circumstance, the mass and the density of the disk is multiplied by that mass. But in the circumstance that we're looking at here,
Print on the GL version?
a high central.
I'm gonna go back to.
And so you would expect a different behavior.
You know, with that, but, right.
If you had 200 solar mass objects in a binary, in this round of a 10 to the 8, you get 2 10 solar mass objects.
Right, so
They would behave differently because what's dominating, and I mean, this is of course before we have this,
but it, like the bridge programs, right, they have a bridge right now. Not always advancing to look.
Literally, I did literally what I said. I said, let us assume that it just keeps having this. That's it. That's all I said. So where does that, what sort of time scales does that end up at? And I mean, out there near the hills.
But yeah, I mean, that's where even things that are hard just to
A couple of orders of magnitude.
Yeah.
That's actually what they're doing, right? But then I have to, but then yes, once you go past that, that's clearly not performance at all. But let's just pretend that it is and see how, like, what's the worst case scenario? That's the worst case scenario.
So that's why we're not saying.
But that's probably right. Something, yeah, there's gotta be a correction for how much mass. And there's gotta be some point.
When I started looking at programs,
Where you're gonna.
I mean, that's not what's required. Where I end up, like where my husband is, easily adjust.
Yeah. What university?
He is at the University of North Carolina. So, yeah. Right. It's in Columbia.
Or not.
There's also a Clemson spot, which is, I hear, pretty good.
Yeah.
Yeah.
There's also because of gravitation.
But it's tricky because for the same reason that I think this is a different scenario because you're talking about a gas.
I mean, I think
it's got an amount of mass in it that is appropriate to the central object, where you've got like a gas disk that's 1% of the central object. Whereas in these circumstances,
But are you saying the density is much higher?
Yeah, well, yeah.
Yeah. No, it's even shorter. Yeah.
What I don't know is
I'm worried about like narrowing out my options too soon.
It is not narrowing, yeah.
I don't know.
Right. So then we come with all right. So right.
Yeah. The limit is only on becomes.
Yeah. I mean, like,
And no,
yeah, I got that has interest in that thing.
Yeah, I got
Right. It's going to be like that messy looking thing like Vlad was showing. I mean, that's
Maybe it's driving. Maybe it is a driving.
Then
Everything's slow.
Okay.
But at least if we close to that, we can see each other often versus like being 14-hour train ride or whoever knows how many hours of plane all they have that like
Great chatting with you.
realistically speaking, we wouldn't see each other often. Being just married, I feel like that's so bad.
Yeah, right. Like yes.
Unless it's self-regulating. But it won't be.
It's not. I mean, you don't have to at all.
No, at least for you to work with. I know.
Okay.
You can see that with this normalization.
The constant is good.
Yeah.
8,000. The next one.
I don't.
Yeah.
Like just not.
I
This normalization of it.
I thought maybe close enough for people, and even if that's a
Which they usually
Yeah.
get for.
He's been helping me like narrow down those advisors and stuff, so it's helpful for me to like just go through this before like filing
Which is bigger than my
after like
bigger than the binary. Even and that's for like a few hundred RG, so then you put it out.
But that's actually like the more ideal scenario than even going through your program. But if I do go through your program, that's
like we started saying.
Yes, but like I mean,
Life stuff.
yes.
Yeah.
Maybe not as much.
And then it's
Exactly.
I'm not sure
I mean,
if
that's why like I'm applying for this because also like
maybe because the
I know
conclusion
later
for me
on
was that
I'm
it's just casting.
like not different programs and clear on
Right.
apply it.
But I think you're right.
Because
I mean,
I mean, that's the thing, right? It's not, you're sort of forcing gas on this binary at a much higher density.
I mean, I think
it's just a specific isolation. So I think that really changes. And it might not be, and the other thing is, I think when I originally did this, I was thinking that even the fact that, so this was the unspoken assumption, right? The having time before you interact is 11 hours. say that that's the doubling time of the frequency, which means that it's not at a constant frequency. So that's going to mess with your
the half timing and the merger timing.
I know that I did.
Almost
and
all
if
of
things
them
pan out, then
the largest.
at least I'll be
but
starting.
not the how many halvings do you need? You need more halvings to get down to 0. If you see what I mean.
How big is it?
In terms of radius.
Right, so I'm seeing the second halving takes
Yeah.
Less.
Yeah.
And the screen program.
Yes.
That's
exactly. They're all true. So I'm just like, I would be like more than so
I think that
they're all
I don't know. Okay, so I mean, because I looked, and basically, if you just read it off of the graph, it says that the time to merger from the top of the Lisa band is
next year.
Is like 1,000,000 seconds.
And I'm anticipating a confidence call because I need to be prepared for that. Yeah. He wants me to apply for this semester. I don't know if it's even possible.
Yeah.
Does he?
the question they are
Oh,
raising
yeah.
was
Oh, I know why.
I mean,
oh, wait, I know why. It's again because I'm doing the dumb thing, and I'm saying it's 1,000 to orbit. So.
Considered doing that before, but if it is possible, I wonder if it might be good for me because I'm a weird guy. I don't know if it would.
Right. So, but if I say that having time is 1,000,
so like, because you're like,
which is what the baritone, like
Okay.
like, you know what I'm saying?
So that's,
I'm doing
that's
a
not right.
dumb thing. I'm doing a dumb thing. I know I'm doing it.
No, but I think the question you're asking is a very good one. You actually have so much gas in
oh, for the policy.
You're gas dominated. And modifying that.
I'm not sure that's crazy.
I mean,
The problem is you have to throw away about it.
Yeah.
Use the realistic form with this.
Yeah.
I feel comfortable applying for a grading program to start right away, but not a huge program right away because I know that.
No, it's not. But I
You
mean,
have to run
Like, I know that that's it's all really interesting, and I want to make sure that I work myself like appropriate. Thank you.
yeah, sure. Oh, yeah, they look like tablets. Yeah. 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 No. I know. I mean, I'm not putting that up there to take it literally, right? I said I'm doing a dumb thing, taking it literally, just to sort of say like, you know, should we maybe care about this? But I think the gas time scale is not the disk that you're going to get around the binaries. It's not the gas disk. This is also why I worry about like extrapolating like Luciano or Andrew's results as well, because it's a different gas disk that forms around that circumbinary. Yes, it's scale 3, but it's a completely different gas disk environment. Like the ratios are all different for these objects that are orbiting. You have higher densities, you have taller sail heights, right? Like this, like the unperturbed disk is much taller than it should be for this little thing. So that's what worries me. Okay, I'll make a point. All right.
Yes. But they feel right now. Also, like applying to great programs, I think myself I have to get everything in order. But at least my CV will be up to date by then. And like having articulated things in my first
parts of it place. I think that's the part that interprets. I know it's the part that interprets because like how personal statement. Yes, like how am I supposed to convince an entire admissions committee? Convince yourself. Exactly. Exactly. Like I know I can do it, but make it. Yeah, I guess you're right. Yeah. Like I believe in myself, but it's like, do I believe in myself enough to be convincing? Like, we'll see about that.
Well, yeah, just give yourself enough time. Send it around to other people.
Yeah. I have these peers in mind, one of them is at this conference, and another friend of mine who's like really good with these things, like at least before, yeah. And like for actual grad applications, I'll like be send it experience at this way.
Yeah,
Until,
definitely. Oh,
yes.
definitely.
Yes. Yes.
Give them time.
Yes. I'm just afraid of like sending something that's like super terrible. So I want to make sure that it's like edited and like whatever.
Yeah, but they will be happy to see more than one draft. I'd rather see more drafts and like have time to iterate than just like things at the last minute and then like, oh, well, I can't tell you anything anyway because
it last minute.
Yeah.
That's the other big thing. I've always just accepted it, but I think I've been better about it, like, as of late. I see the progress, and like, I know I'm capable of being good about this. So, yeah.
Good luck with these this year.
That's amazing.
Yeah.
Thanks.
Yeah, so I'll see you tomorrow and if you want to send me any materials you have. It's good to actually to see what you've been working on recently so I can update my priority stuff.
Oh, sure. I mean, it's every year.
You did, yeah.
Send you like my poster from WS maybe this winter that has more.
Or your
Embarrassing as it is right now, but okay. I'll do that.
Cool. All right, I will see you tomorrow.
Okay, see you tomorrow.
Oh.
You know how Zoom is recording, right? Will we be able to look back at recordings of of certain sessions and stuff? Do you know where we might be able to access it?
Ask the woman who's the staff person at the desk,
Yeah.
Melanie Sherry.
Yeah.
Ask her.
Cool, thank you.
Yep.
Thanks. Yep. To return to the same point.
Yeah. Well, sure. You know, you gotta keep hammering away.
Yeah.
Forwarded you.
Oh. Okay.
Forwarded.
That was the one where they get it for US 10 to the minus 6 or something.
10 to the minus 4, but yeah.
Yeah. Oh, 10 to the minus 4.
Yeah.
I thought I understood like you couldn't get gap opening even as low as.
That may or may not be. They actually only did 10 to the minus 4 in this paper.
And they have an alpha of.
They vary their alpha all the way from 3 times 10 to the minus 5 up to 50. Yeah, but actually, frankly, you don't get much of a gap below 10 to, until you drop below 10 to the minus 3. This may not be relevant to us.
Yeah, but that's also useful for maybe for the observables tomorrow. Right, just bringing up that points.
Yep.
Right, depending on what we think our alpha is, do we get a gap at all? Right?
Yeah. Well, here's a relevant plot.
Okay, sorry, I'll be back. Just.
That's more like this. That very last talk.
That's 2D.
Yes.
And pay appropriately.
Yes.
Depending on writing. Reading thesis.
You want us to be?
Yeah, this is for an empty mass planet. Cube.
Yeah. It's still not. But still.
Exactly. So you
For us.
Yeah. So.
So type 1, type 2. Yeah, you can make that work. You said you wanted to put something back in, you want me to go?
Yeah. Yeah.
Yeah, it is a local.
Start.
Yeah, man.
I'm not sure it matters so much.
Convection in ice.
Compaction in ice.
Convection.
Oh, convection in
And
ice.
ice. Nice, huh?
Cool. Where? Ice on
Europa, yeah.
Oh, nice.
Let's see.
Quick one. It's the same model that we did before, but the referee thought that the previous one was low resolution.
Yeah.
So we cranked that by a factor 5 and burned like 2 million computer hours.
Jesus.
So now I am without.
Like I had to email my slide work.
Did it make a difference? Qualitatively, no, but.
But Amy could.
Qualitatively, it didn't make much difference. You know, it's what we needed to do. So hopefully now we can publish the paper.
Is it still more C++? Yeah.
All right, we made it back to the methods.
So, here we are. We've established that the problems are difficult. So, that's useful in the sense that it gives us a field of play, but I think now I'm looking for a discussion of where to go next. So I just threw up some thoughts. techniques, but we're trying to model at 3 scales. So there's the structure of the disk, that is bringing stuff into the disk and understanding what its time variable structure looks like, including thermodynamics, which is tough because now we have to start worrying about variations in cooling and variations in opacity with temperature, because those opacity transitions can drive the formation of migration traps, do drive the formation of migration traps. Once we're in the disk, we then are trying to assemble subgrid models that will allow us to model the evolution of systems of orbiters. But in order to model systems of orbiters over substantial fractions of the disk lifetime, we can't follow, every horseshoe turn around each orbiter. So we need to model what the effective torques on orbiters are in different situations. And then there's the whole set of questions that several people have emphasized of what happens when 2 orbiters come close to each other. How, in detail, does a binary form and evolve under the influence of the larger gas disk and the local behavior and any passing other objects? So where do we go from here? Brave.
So I'm gonna.
Yeah, sorry. Just push it once.
Yeah, got it. Okay. Is that working?
No. Yeah.
Okay, cool. So I think actually just out during the coffee break, I was chatting with Sultan and also with Andrew, and I think maybe a useful point here is that, well, there's 2 parts to it. So once you have a binary embedded in an AGN gas disk, the gas that matters for driving the binary to merger, or that may matter for driving the binary to merger, is all the local gas. And so in some sense, that's good news for modelers because you don't need to have the entire disk drawn up. You just need to model the local gas. However, the gas that is going to act on a binary, a stellar mass black hole binary that's embedded in an AGN gas disk is not actually going to have the same structure as if you were to take 2 supermassive black holes and put them at the center of a circumbinary disk. And of course, we can worry about the shear, but the bigger issue, I think, is that the disk that's going to be around 2 supermassive black holes, it is the right size. It's the right size and the right structure for that central mass. Whereas if you have a 10 to the 8 solar mass black hole in the middle, and then you have 2 10 solar mass black holes in the binary, the scale height is going to be, the scale height of the gas that it's embedded in is much larger, and there's going to be much more mass. And so you have the potential to be, as actually has come up several times at this point, you have the potential to be attempting to shove vastly super Eddington amounts of gas into this binary. And so that's, of course, going to change the torques, the hardening torques on it. And then, of course, we have feedback, because, again, the good news, bad news is the only gas that matters really is the gas that's very local. So, but exactly where the feedback goes and how that does or does not alter the gas density, therefore matters a great deal for how efficiently the gas can harden a binary. And so I think those are some, I think some of those questions are more tractable than others. Andrew, I don't know if you want to say some more about.
Yeah, thanks. Yeah, I agree that it's a really interesting problem. I think the last talk was probably relevant. So if there's a scale height of the AGN disk is much larger than the characteristic size of it, and it's also optically thick, then you're in a very different type of regime. You have gas that's kind of almost like an ADAF. So so it might be more like this. So yeah, I agree that it's a different, it's not true that we should take the results from circumbinary accretion and plug it into this case. I think there's some similarities and we should understand one in order to inform the other. But I think there's 3D effects are probably very important, probably radiation transport.
At least it has 3D effects.
Yeah, I know, yeah.
But as a model for how to implement this situation, not as a model to draw information from.
So for example, I would say that what we're trying to do is kind of a model problem. It's very simplified in 2D, and it is true that we're getting positive torques for this particular case, but I wouldn't take that too seriously yet. I think it's just something to keep in mind. And it could change a lot depending on the environment, on radiation transport, on MHD, lots of things.
So I think, with my pessimist hat on, I'd say that, what we want here, fully 3D, MHD, full disk, multiple N bodies plus radiation is effectively impossible. That's the bad news.
Yeah. Not only that, you wouldn't necessarily learn anything from simulating it.
Exactly. The good news, I think, is that we can get a qualitative sense of what happens, and we can hope to extrapolate by doing simple numerical experiments in idealized cases, changing one thing at a time, and seeing what the effect of varying alpha or varying H over R is in particular cases, and then attempting to sort of build that into our intuitive understanding of what might be going on more generally. So, the good news with my optimistic hat on is that I think a lot of progress can be made in the next few years if people keep on the paths that we're going on. Something that came up in the discussion at coffee, I was chatting with Andrea and Dan, was, if we can come up with numerical studies that we can then develop a sort of semi-analytic framework that maybe we can apply to, say, 2D simulations, which are less computationally intensive and maybe mimic the 3D effects on a 2D scale, it'll help us move faster and maybe investigate some more of these problems. But
so yeah, I think that's the right. Oh, sorry, Dan. Okay. That's the right approach. I advocate simple as possible. Try to understand it, analytically capture it. I don't agree that going to the more complicated simulations is a good step. It can just be confusing. So yeah. Yeah. I thought you had your hand up. No?
Yeah, I'll say something.
Did I do my job here?
You scared us all.
Go ahead.
Yeah, it's kind of a question for you, Andrew. So in the 2D case that we're still trying to understand, what do you think will be the point where we know we're right and can move on? I mean, it's kind of an open-ended question, but...
Let's see. So we're not going to be right with the capital R. We're going to be right for that particular set of parameters that we're studying. I think we're kind of close, but these are big computations even in 2D. So because they involve thousands of orbits and they have to do it at very high resolution, you have to try to resolve as close to this go of the holes as you can. So, but we're looking at convergence, and we are starting to get some things that converge. Not everything converges, but some aspects of the problem converge. So I think we will understand things like how the accretion torques, how important those are, how they compare to gravitational torques, what the sign of gravitational torques are for a certain set of model parameters. And then once we understand that, then we can, I think, start to try to add just slightly more complicated physics and just do that incrementally.
I can go for the mic.
Yeah, okay.
Don't worry. Yeah, one interesting difference is that, for example, if you look this small plot at the right, the one with the blue, yes, no, above that one, you see there this is the binary in the three-dimensional case, and in this case, the evolution of the binary, the shrinking of the separation is super fast. It's like 4 orbits, 5 orbits. So it's not like you have, in this case, I don't know if you have to understand if you're doing it right, the modeling of the torques and how evolve the binary, you have to run something to super high resolution maybe to see this shrinking very until the end. Or no, because you put the binary there and then it shrinks super fast, so it's not, yeah. So no, I think that super optimistic for gravitational waves, but I don't know.
That would fit with Amy's assumption of that would match with Amy's prescription of, you effectively form the binary and then it merges, right? It's super optimistic, but
yeah, this will be maybe in the case in which you are more optically thick, more dense. Maybe in the low accreting supermassive black hole, you will have a low density gas, and you will be in the other case. But yeah,
right. I should get you a Yankee sat.
Yeah.
Zoltan.
Zoltan.
Yeah.
Okay.
Yes.
Okay.
Yeah, I got it. I made Zoltan run. I should run.
I was gonna try to answer Dan's question. So I think we can move on when you demonstrated that there's numerical convergence, meaning in terms of time steps or spatial resolution, and when two codes, when given the same exact problems, give you the same exact answer.
That's a good point.
So for example, today we heard 2 talks which showed when you make the binary live, the torques become smaller, and then we heard another talk which said you make the binary live, the torques become bigger. And it's just confusing. Of course, it's possible they have different parameters.
Comparison. Yeah.
So what this naturally leads to is this, the idea that there should be some comparison. Given exactly the same initial conditions, same parameters, people should run their codes, and this can be tricky, but
For example using AMR code in a single grid code.
It happened in other contexts, like the cluster community had this famous Santa Barbara cluster project, and it can lead to a lot of politics and complications, but the end result, I think, in that case was very good because people started, I think, believing the cluster simulations.
And yeah, I would just,
I'm not sure it is the right audience for this proposal, but...
Yeah. On that, I would just add,
depends on what, I was gonna just say that maybe that calls for establishing a sort of benchmarking problems that we would like to see.
That is exactly actually what I was going to say. So if we can put there, can I show
Yes.
in there?
Let's see, you can grab AirPlay if you have a Mac.
No, I can just put there in the Dropbox, that's fine.
Okay. I can also probably call it from the Dropbox. Let's see. I bet you this is it. Yes. Let me know when it's in.
I'm looking for the file.
Anybody want to make a comment while he's searching for his visual? Yeah.
Another question is, what is the initial condition? So even if we converged for a particular initial condition, how do we know that we were running the correct initial condition? Because, it might take many viscous times to reach
That's
the
there.
correct.
So pull up. It's a PDF. I just put there in the. So this is a project that we had a conference on it back in 2017, in the end of that year. And we agreed on 4 problems on 3D models of planet-disk interaction. It's basically an update of a code. Well, yes, that last one. So it's an update on a work that was done in 2006, but now with modern codes and new problems. So we are still collecting results for this. So if you want to run these benchmarks and give to us, there's time, right, to add them to the article that we hope to soon write about it. So there are 4 problems. They're testing different things. So the main things that we're testing for are non-isothermal torques, migration, right, like both negative and positive. So the initial conditions for each one of the benchmarks is detailed there. Mordecai, if you can scroll down more, because I don't remember what now the last problems are for. Yeah, right, okay. So yeah, like 3D, non-isothermal disks, and moving planets. Right. So.
Okay. Great.
So what happened? These 4 groups have done this? Or?
No, these are 4 benchmark problems, and we invited anybody with a code that can do it to contribute their runs, and then we are going to do a comparison between all of the codes that run these benchmarks.
Did you have any preliminary results?
Yeah.
Okay.
Are they?
Oh, you want me to show it?
Yeah.
Well, I mean, in terms of comparing 2 or more.
Yeah, we already have 3 groups. We already have 3 codes. The Nirvana code, the GFargo, and I forgot the Athena code. And my group is doing the pencil one. Yeah. So far, so good. I mean, like it seems that like no issues yet have been found between the different codes.
Reassuring.
Just because I'm taking notes here for the summary, can you just, you said there were 4 problems, but I only heard 3 listed.
Okay, short run, high resolution. Go ahead. And this will be in the Dropbox too. Short run, high resolution, long run, middle resolution, adiabatic disk, and moving This is a moving planet in 3D or 2D?
2D.
2D, okay.
So you should be able to do that, Andrew, right?
Yeah.
So at the risk of getting a little too technical here, I think what Andrew already mentioned is what we're finding is the sink is absolutely crucial, how you treat the sink. So I'm actually not off the top of my head sure how you make that uniform across codes, because their sink treatments are different. You know, how you remove mass. Or was that an issue in these problems, or has that been?
That we cared about removal of mass.
It completely changes the migration
And
results.
then we would need to add.
Frankly, though, if the sink treatment matters, you probably need to think more about how you can push down to the resolution where the sink isn't determining the behavior. And that's an important numerical question, because the sink is an approximation. And so you need to think about what does that approximation, what does that subgrid model actually represent, and how can you make it robust? We face the same questions in star formation, obviously.
Yeah. So we did do that. Yeah. Right.
For you?
Oh. Is it too hopeful to think you can just parameterize your uncertainty and then think of observational ways to constrain accretion efficiency? Yeah. I mean, I guess we do that with all the other disk parameters too, but maybe like there's some implication if there's a lot of feedback or if there's not, or if there's
We have a much
efficient.
less ambitious goal of just making sure we have the right numerical answer for some toy problem.
Well, we won't really know if it's right until we confirm it, so we should have.
No, numerically right.
Yeah.
Oh, I see, that kind of.
Yeah, so we just want to.
I get it.
For initial condition, it's just any
We did-
initial condition, just make sure we get the same result.
Yeah. And then we can check things like the sink size. Do we converge as a function of the sink size changing?
Sure.
So there are a lot of technical things that require a huge amount of work and a huge amount of computer time actually just to get a technical result. But then hopefully we'd be able to describe it in terms of a analytic prescription, hopefully, yeah.
And certainly in fields that have run comparison projects, this sort of work has led to a great deal of confidence in the technical results, which has then pushed forward the scientific results. And I would point to, galactic clusters, galaxy clusters as a classic example of that, where now that we have a really solid handle because of those comparison products, there's been a lot of good science, understanding how they actually work.
I'll throw another cat among the pigeons. I'll throw another cat among the pigeons. So far this conversation is basically, since the coffee break, we've been thinking about what happens to gas in a binary. But it's certainly come up repeatedly that collisions will probably, well, at least we have to worry about them and show that they don't matter or decide what to do about them if they
You mean
do matter.
tertiary interactions?
Tertiary interactions. Obviously, we've done some work with that, treating things, we're just worrying about the black holes, but as Haggai has said already and others have pointed out, that there's a lot more other things that are not black holes. And I'm just wondering if anybody has thoughts about how to make progress. What are the priorities for making progress on those issues and in that direction? Does anybody have?
Well, we're going to have to develop a subgrid scale model in order to be able to do the sort of Monte Carlo models that will probably be required for this, unless we can put together an analytic framework, which is, what people like Nathan try to do. But do you want to?
One thing you can do is actually in the Galactic Center, we do have observation of low mass X-ray binaries, right? We can constrain, and we know more or less the lifetime of the disk that was there, the density, just from the stellar disk that we see today. So in principle, we can already constrain quite several models from just from the formation. We don't see the low mass X-ray binaries in the disk so much. So I don't know how many of them were supposed to have formed, but in a sense, you can actually do this calculation in any model that you have, then compare to observation. So So we can actually do some direct comparison with observation even today in the galactic center for a short-lived disk, because we know it couldn't have been, this is not like a long-lived AGN disk, but at least at this scale we can actually study this. So, did we have any CVs which were consistent with being in disk? Because CVs would also form the same way. And we had many more of those, I think, in the Galactic Center.
I thought that Kaya said that it was spherically distributed.
Right, so the question whether, they looked actually for any overdensity in the disk area, for example, something like that. I don't know.
And also, I don't know if they might be more likely to be scattered, so how long would they persist as a disk after the dissipation?
I give you the simulation.
Yeah.
It persists, it could actually, you can still see the disk even 100 megayears later be buffed up, and you can still see it. And we're talking only 5 megayears later.
Okay, from the mic, please.
So sorry, even.
Mic.
Yeah.
Sorry.
So we did simulation of the evolution of stellar disk over a long time scale. So first of all, 5 megayears, you can see the disk today, so the CVs should not be much different. They're lower mass, so they're scattered a bit higher, but not much more. But even after 100 megayears, you still see the kinematic signatures of a disk like that. So in principle, we can even constrain past disk if they were there, to some extent using it.
So, I now, having had a chance to look at Duffel and McFadden, I now understand that you were finding gap opening for alphas of like 10 to the minus 4 and less. Is that right? So that's probably relevant in a disk where the ionization has been suppressed for some reason, protoplanetary disks, or maybe the very outer regions of AGN disks, or do you ever get down to the low enough ionization that you're dropping your MRI? You have to be at like 10 to the minus 6 ionization fractions.
I know nothing about AGN disks.
Fair enough.
So alpha should be quite a bit higher, obviously, in AGN disks. So I think in the Duffel and McFadden paper, the gap doesn't open for alpha is 0.01, right? And so you'd easily get that in an AGN disk.
Wait,
so
it does not open.
It didn't open, right?
Correct.
Remember? Right.
Yes.
Yeah. So yeah, experiments with alpha are sort of interesting, but for this problem, we'll want alpha to be pretty large in any simulation that we're doing.
So even in the midplane of the disk, it's large.
There's a big radiation source there.
Yeah. Yeah, I mean, so the latest from changing look quasars, which may, to be fair, be a subpopulation of quasars, they may be the most extreme. But basically, we see changes sort of rippling through the disk, which imply a viscosity of maybe 0.1. So, these things have high alphas and probably pretty high aspect ratios, at least at the changing look quasar end. We're not talking Shakur and IF. Right.
Which will also have implications for the possibility of building up these the stellar mass black hole disks, whether you'll have some sort of, you want to? Yep.
Just wanted to ask another question. Can someone comment on the recent Moody paper? Like, what are the differences with respect to previous results, or should we believe them, or?
Sorry, which data?
This Moody paper.
Oh.
Yeah.
The Gemstone group.
The positive torques.
Yeah. So I mentioned that the first day. Yeah, I think they use what we call a fast sync, and they get positive torques, which is what we also got. So it's consistent. And then I guess the most exciting part of the paper to them anyway was that they were doing 3D. And again, yeah, it's always nice and fun to go to 3D.
Did you want to add anything, Vlad?
Oh.
Yes. On Mooley.
Sorry?
On the Mooley et al. Paper.
Moody.
On the Mooley et al. paper.
Oh, I'm sorry.
Moody.
Moody.
Mooley? This paper on the bottom
No, it's a
right, the gap
different paper.
opening?
No,
it's a different one.
Oh, I'm sorry.
It's the one that I mentioned the first day. It's
I
Moody,
was-
She, and Stone.
Oh, sorry, totally misheard. Well, go for it.
I'm just going to highlight something that Andrew just said because I think I understood a little bit better something that was said earlier. But so you just said that in the Moody paper, the sync, they used a fast sync. And so that is part of what's giving them a different result. And so just if we're thinking about benchmarks and emphasizing what Zoltan said about the sync treatment matters. So there.
Yep.
We stop repeating ourselves, and I'm trying hard to avoid my rant about this subject. But
sorry.
I'm trying to avoid giving you my rant. But
Go ahead and rant a little.
but basically, Andrew already said yesterday that when we vary the sync speed, the torque changes. So slow sync gives you a in spiral, fast sync gives you an out spiral. I think the best thing to do for everybody is to look at the plots in the papers, or maybe I could flash one up, but basically it's very obvious on the plots what's happening when you do a fast sync. You actually eat the middle of the mini disk, and you punch a hole. It's clearly something that doesn't look physical, and all three papers have when we have this hole, we get the positive torques. And then when we don't have this hole, because we slow down the sync and mass is allowed to pile up, then we have a negative torque. This is
Once your sync is swallowing structures important to the problem that you're trying to examine, it's time to consider what your subgrid model for the sync should be and how to modify it. I mean, just like if you want to know what the IMF is, you can't swallow the entire inner irradiated disk where fragmentation is occurring with a sync. The same here. If you want to know what the torque is on the black hole, and it depends on the structure, the inner structure, you can't swallow that with a sync. I think that's an important conclusion from that series of papers, but that's not a problem with the syncs per se, it's a problem with the use of the approximation.
Yeah.
Richard?
So to follow up on your comment, so what we did do in a second paper with Tang is consider the case where the ISCO is being resolved. So in that case, the fast sync is the appropriate physical model because the gas is plunging in the ISCO.
Assuming that the ISCO is the innermost region, as opposed to the observations which were shown on the first day, which seemed to imply that the disk is somehow further out.
Oh, right, okay, yeah, yeah, that just makes it more complicated, but yeah. But assuming that we're resolving the region that is physically being depleted by the black hole on a rapid time scale dynamically, then those simulations are good.
Oh, okay. Try typing it again. Yeah, go ahead. There we go.
I'm not sure I have anything to say other than show this picture.
You can make it bigger.
So this is our paper with Andrew, and this is how the surface density looks like if you have a what we call the normal sink rate of a local viscous time. This is what it looks like when we have this artificially fast sink. So you see, you create this hole. Then this is a paper which claimed a positive torque and claimed that they disagree with our paper, but in fact they completely agree with our paper because they, like us, found a positive torque in the case of a fast sink. So here's their, they don't vary the sink speed, but this is their surface density distributions with these holes. For me, that's very convincing. And then here's the Moody. This is from the, this is this paper, which just came out 28th February. And this is a little less clear, but again, it looks like they're in this regime of they remove mass too fast.
Yes, and so I think it's also the fast sink. Somewhat confusingly, they talk about it as being a viscous sink, but it's a local viscous sink. So that's R squared over nu, and they go all the way to the center where R squared goes to 0. So they have a very fast, effective sink.
So they did compare with your paper, Yaki's paper, and I thought they directly
Hang on.
compared.
Hang on.
Yeah, we can't,
Yeah. I only skimmed this paper, but they compare, I thought, directly with the sink timescale and Tang et al., which is the paper that you're mentioning. So do they state explicitly what the sink timescale is relative to the one you use?
I actually didn't look at the revised version. They might. In the Munoz paper, they don't state the sink timescale at all. They don't seem, I don't know what they're doing. They're using some sort of, it's from a repo, which has a sink particle. Okay. And so there's some sink prescription that operates on a time step. Yeah. So I think it's effectively a fast sink.
Right. Yeah.
Which you can kind of see from the holes all the way to the right there.
Yeah, we can check it. Just it must be in a number in the paper. So
I would say the conclusion from these 3 simulations, these are 3 totally different codes, and they all agree that the torques are positive for a fast sink, which is what we said.
When you're positing a fast sink, is that including a treatment of the inevitable radiative feedback that's got to be dominating?
No. And that,
Just check it. Just check it.
So yeah, simple. Yes, that could completely change everything. We do this.
See Krumholtz et al. 2005.
Yeah, this is a model problem without radiative feedback.
So I just looking at these 3 plots, I would love to know what this looks like if you keep everything the same, but you embed this binary in a shearing flow. Right, don't make it circumbinary, just have a shearing flow and see what happens. Right, that would be a lovely thing to do.
Basically adding the Coriolis force, right? Thanks. No, yeah, I mean, like, it's basically redoing that in a local box, right, with the Coriolis force and shear. Going back then to the accretion thing, I know Willie Cly was doing that, right? Models with giant planets and accretion onto the planet, and I know that he saw also that it would change the torques depending on how big the accretion radius was. But that was, I mean, the last time that I heard anything about that was in the mid-2000s. So the community seems to have just dropped that because it's not being done anymore.
So we were talking at coffee about what's happening through interest in the AGN channel is that we're starting to feedback onto the protoplanetary investigations. We're leading the way in a lot of respects. So what we're doing can really impact on protoplanetary studies, which is really awesome. It's great to see.
It's a two-way road, right?
Yeah.
Yeah.
So if you have an embedded binary and it carves a gap and there's gas flowing across the gap, this is inherently different than the circumbinary case. Don't you need to have a global simulation to something like this? Because you have gas flowing near the binary, but on horseshoe orbits going around, it's not axisymmetric. You need to have like a global, yeah, like you need to simulate the whole disk. You can't just have a shearing box. It's a question.
So first order, yes. Yes and no, right? Yes. So you can approximate it in a local box to first order, right? I mean, you would have flows there from both ways, and yeah, I mean, like you can do that. The question then is to understand exactly where the approximation breaks down.
Sure.
I just had a question. If any of the simulators looked on the Anthony paper about the binaries in disk. I think I talked with Andrea about it, but I was wondering whether you have any comments about this paper. It's about binaries in a gaseous environment.
It's a common envelope moving in a wind. So
Oh.
that's the
Anthony McLeod and Enrico.
Morgan McLeod.
Yeah.
I've talked to them about it, but I'm sorry, I didn't look carefully at the paper, so I can't comment.
I have one point there, yeah. Yeah. One point there is that they do this experiment of the binary inside a wind tunnel at the end, and it's a common envelope, so you don't have the formation of the cavity, and they compare the accretion in a wide binary or a closed binary, and they see that the accretion change in the you have two regimes, one in which if the binary is super tight, the total accretion of the binary is compared with the Bondi accretion of the sum of the masses. But if it's wide, the binary, then each body accretes like Bondi, more or less. But obviously here they use one prescription for the same particle. And so I don't know how that will change if you change the same particle prescription. And the other thing they conclude is this hierarchy between the timescales, in which you have the wind that will stop the center of mass of the binary faster than the shrinking timescale of the binary, and that is faster than the accretion rate timescale. So at the end, if you naively take these timescales, you will see that accretion will have less an impact there than shrinking, and that will have a less an impact than the sinking timescales toward the supermassive black hole. But this is only a binary in a wind tunnel at the end. So.
But it's not. But this is what we have, more or less.
Yeah.
This is what we actually have. I mean, the cavity. This wouldn't make a cavity unless you're in the maybe last stage where it's facing this.
Totally.
Most of the time, you're really in a
wind tunnel. Yeah. I think that's the thing. But here you're only taking the dynamical friction onto the center of mass. So it's different than if you have a torque zero trap in the disk. I don't know how that will change if you take the total torques of the disk. But maybe yes, maybe yeah. But the important thing is that they have this hierarchy between the time scales of the processes, so that tell you something about what will be more important.
So I was just going to say back to Andrea's point earlier that a key component of the hardening is going to be from the gas within the Hill sphere, just the gas within the Hill sphere and the dynamical friction there. So that does not necessarily require a global disk. I mean, that doesn't require a global disk simulation. So
that flow comes from gas.
If you need to resupply it, right, yeah.
So I was just going to jump in on Luciana's point. Yesterday, Carl.
Let's let Vlad go next.
Oh, sorry.
Oh, okay.
I was just going to say, yesterday, Carl, in passing, kind of expressed preference for this channel over the common envelope. In discussions, there was a sense that you preferred aspects of this channel. I just find it really funny that we may end up discussing common envelope situations where these things are embedded in AGN disks, and we may end up dealing with the same bloody problems.
Yeah. I'm out. I was just going to say here that I found here what Willie did back then. So what Willie found is that the torques change with the accretion radius because they change the mass accretion rate. But what is actually changing the torque is the mass of the planet. How wide you make the accretion radius impacts the mass accretion rate onto the planet, and then by implication its mass, right? And then that will impact the torque. Are we talking about the same thing in your models?
So it's the mass of the...
Yeah, what is happening is that if you change the mass accretion rate, you're changing the mass, which changes the torque.
I'm not sure that's what we're finding. I think it's a different thing. Because, yeah.
No, not particularly that. That said about the accretion rate, the accretion rate on the orbit.
Going once.
Question.
Oh, maybe also. Yeah. Yeah.
So did anyone do simpler simulation, not a binary, just a single star in this disk? Does it form an accretion disk around it? A big accretion disk?
A single star or a single black hole?
A single black hole, let's say.
Yeah, they do. It depends on the mass ratio between the central black hole and the secondary.
Yeah, it's the helio disk.
But I think
that's fine, huh?
Yeah.
That depends on the equation of state, and thus the cooling properties and the feedback.
Lots of things.
Which Luciano pointed out. But if you have a black hole embedded in an optically thick disk, I think there's maybe some question as to how much of a disk it will form. Now, there's this Sulyagi paper that is claiming protoplanetary disks, even around Neptune's. But frankly, I think there's some questions about the cooling there as well. Isn't that right, Vlad?
Sorry, can you repeat your question?
Aren't there some questions about the cooling around the proto-Neptunes that Sulyagi was computing, and whether those protoplanetary disks are actually, those circumplanetary disks are robust?
The only thing that I remember about cooling, so how cooling impacts that is how fast you bring mass onto the planet, because you need to accommodate mass to it, right? Before you can add more mass. But I don't think that in the black hole case that will matter, because any gas that goes in will be...
But you still have to satisfy, you have to get in through the radiation pressure.
Then that's a different thing, yeah, because what is happening there is that the gas pressure does not allow the gas to collapse on the envelope of the planet. So the gas has to cool down, get denser to make room for more gas. I imagine that in black holes you wouldn't have that problem.
I think you would have that problem.
Yeah. Yeah, I mean the problem is like, yeah, we'll have a lot of radiation being generated, and so it's going to be hard for this gas piling in to cool down, and so that led to Zohan's point that maybe it will be swallowed with the with the inflow, right?
Right, so you need to know the opacities of the gas quite well. That was a problem in protoplanetary disks that lasted from the Pollack model of 1994 until I think that the first model that showed that you could make a giant planet within the lifetime of the disk was in the late 2000s. So that's a pitfall there.
So the nature of the AGN, once again, the nature of the disk that we're considering, as Luciano was saying, right? That's key to how the gas is going to accrete, right? What is an AGN?
Wearing your Mets hat yet? One piece at a time.
Okay, so I'll just ask, I think I said this earlier, is it enough for AGN disk models for the purposes of this project? We would like to know the density and the scale height and the lifetime, and I think now it sounds like I need to add the temperature and the mid-plane temperature and the composition, potentially, depending on the opacity sources. Is that fair? Fair list of requests?
At least for the region around the black hole, the stellar mass black hole, yes.
Okay.
So what's really fun is if you think about the supernovae that are going to enrich the metallicity in these things, right, and change the opacities that we need to worry about.
Any individual supernova is going to make a small change.
Yeah.
I have a question there. Yeah, sorry, because you're talking about like stars that will be inside the accretion disk, but my guess is that stars will lose part of the mass because of the interaction with the accretion disk because it's super dense. So maybe you will stop some of them to explode even, or not?
Yes. So this is, I mean, we can discuss this in the observables session, but like if you think of the mass loss from massive stars and how fast it is, that's nothing compared to the orbital speed of the objects embedded in these AGN disks. So you'll have this weird, funky interaction.
That's going to be important for a retrograde, but for a prograde, it's going with the flow.
Yeah, that's true.
So
that's true.
I guess you'll have the pressure support, which is a few percent, and maybe the velocities are so high that even that few percent becomes important. But it's a hot disk, so I imagine the sound speeds it's still going to be subsonic.
Yeah, it should be subsonic. Yeah. Matt's hat back on. I think I need more Matt's hats.
I think we should call it.
Yeah.
Thank you all for your vigorous discussion.
Thanks, Mordecai.
Yeah.